So we've talked about logs in terms of their existence as the inverses of exponentials, but in order to talk about them as functions, which means, yes, we're going to explore their graph a little bit, there's some details that we should make sure we understand. For starters, it is the inverse. By design, this is the inverse of an exponential, which means that its graph is going to be the reflection of the exponential graph in the line y equals x. That base, whether it's y equals b to the x or the log base b of x, that base b is the same value for both the original function and the inverse, whichever direction we're going. Along with the inverse idea comes the swap of domains and ranges. If we're looking at the domain of the log function, that's also the range of the exponential that is its inverse. If we're looking at the domain of the exponential, that's also the range of the log function that is its inverse. And vice versa when we talk about range. Range becomes domain. Details that we have out there. Now we should take a look at what these graphs actually look like. What we have in this image is we've got the line y equals x representing that line of reflection, and then the graphs of both y equals 10 to the x and its inverse y equals log x. Now, we don't write the base when it's base 10. Log x is referred to as common log. Common log because it relates itself directly to our number system, which is base 10. The only time we need to write a base value in there is if it's not 10, kind of in the same way that we don't write the 2 as an index when we're taking a square root. It's just assumed to be the 2. Well, when we write log, the absolute only thing it is, unless we write some other b, is 10. So let's take a look at a few things that would pertain to these graphs and use them as a basis for what we know. The generic parent curve is going to be the log base b of x. That b value can change, and it changes the shape of the graph slightly. There's a vertical asymptote now. What once was the horizontal asymptote for our exponential function reflected over the line y equals x becomes a vertical line. So there's a vertical asymptote at x equals 0. We pay attention to 3 very specific points in order to get this graph created. The point 1 over b, negative 1, the point 1, 0, which we can see in the graph of y equals log x, and the point b1, which we can also see in the graph of y equals log x, because in that case, remember, b was 10. Now these are direct reflections of those same points that we were working with when we graphed the exponential function. Last details that are important are domain and range. The domain of a log function, well, if we look and we know that it has a vertical asymptote at the line x equals 0, and it exists entirely to the right of that, its domain is going to be 0 to infinity. Its range, well, it continues down forever on the left side, and it's going to continue increasing on the right, however slowly that might happen, but continue increasing, so our range becomes negative infinity to infinity. So if it were log base 4 of x instead of log base 10 of x, what would it actually look like? Well, we start building with those same 3 points. The b value is 4. That's the base of the log. It's the base of the exponential. This is the inverse of. So we'll replace b in that 3-point cookie cutter with 4. So we get the point 1/4, negative 1, 1, 0, and 4, 1. Now, we plot those points, and then nothing's changed about location for this graph. So we'll identify the fact that we still have that vertical asymptote at x equals 0. Now, once we're here, you can see the shape that this graph is taking. And we'll sketch the curve. Domain, well, it exists entirely to the right of that vertical asymptote, so our domain is going to be from 0 to infinity. And our range continues down forever, continues growing forever to the right, negative infinity to infinity. Now, what could possibly impact these things? Well, we have to take a look at the entire family of log curves. Yes, this is where we talk about transformations. Now, all we're going to be doing is putting variables in place where we know that they already have an impact. It's just we haven't seen them in this format before, with the log function as the argument. So our parent, restrictions on our parent, same restrictions we had when we were dealing with exponentials. B has to be positive and B can't be 1. Yes, that means that we don't take logs of negative base values. So y equals a log base b of x. Well, we know what a values do. When the absolute value of a is greater than 1, it's a stretch. When the absolute value of a is between 0 and 1, it's a compression. Now, that's both vertically stretched and compressed when it's an a value. When a is negative, we get a reflection in the x-axis. How about some translations? Y equals the log base b of x minus h. This is a horizontal translation, paying special attention to the fact that now our crazy house actually exists inside of that log expression. Y equals log base b of x plus k. Well, k is always signified vertical translations. Notice how there are no parentheses here. That k is intended to be outside of the log expression. Log base b of cx. I needed another variable to use as a multiplier inside of the log. Now, when absolute value of c is greater than 1, it's a compression. Between 0 and 1, it's a stretch. These are horizontal stretches and compressions because they're acting on x. They're part of the argument of the function. And then when c is negative, it's a reflection in the y-axis now. Now, if we put all those things together, it becomes a large string of variables. Nothing we can't handle. We've seen all of these things at work before. Now, the ones we really need to pay attention to in terms of domain and range are horizontal translations. Well, if we slide the entire asymptote. If we slide the entire asymptote, we're moving that boundary that was identifying one end of our domain. And when we reflect in the y-axis, now if we reflect in the y-axis, this flips the curve backwards as compared to the way we saw it. Instead of being entirely on the right side of the asymptote, it would be entirely on the left side. This is going to reverse the direction of our domain. We need to be able to identify the moving parts. So we have the log base 5 of x plus 3 minus 2. In terms of transformations, things that we see here, well, x plus 3 says that it's going to slide left 3 units. Subtracting 2 means we're going to slide down 2 units. What does that do to our asymptote? Well, if our asymptote used to be at x equals 0, then now it's at x equals negative 3. What impact does that have on our domain? Well, our domain used to be 0 to infinity. Now it's going to be from negative 3 to infinity, keeping in line with that vertical asymptote. Visual confirmation of these things. We can see that left 3 and down 2, those points on the blue parent curve, become the points on the red new curve. And that vertical asymptote, what used to be at x equals 0, is now at x equals negative 3. What about y equals negative log base 7, x plus 1 minus 5? Again, we get the rundown of transformations. We're going to be reflected in the x-axis. Left 1 unit, down 5 units. How does that affect the asymptote? Well, if I go left 1 unit, my asymptote goes left 1 unit. So instead of x equals 0, it's at x equals negative 1. How does that affect the domain? The asymptote is a boundary for our domain. The boundary moves left. My domain extends to the left just slightly. same appearance to our image. We've got the blue dotted parent curve. The orange X's are after the reflection, and then we see them move left and down to become points on that new curve, the red curve. And the asymptote pushes itself back to x equals -1.